Hello everyone, and welcome to today's chem lesson. Today, we are going to talk about intermolecular forces, which is a concept that we're going to look at as we zoom out from looking at bonding, which is an intramolecular force, right? If we look at something like CH4, these bonds are inside the molecule. We want to take a step back and say, how does this whole molecule interact with other copies of the same molecule? If I have other CH4s, what makes these things stick together, fall apart? How do they behave when they are near each other? That's the question that intermolecular forces is going to answer. We're going to look at the interactions between two or more molecules. There are three types, and we're going to look at them in order of weakest to strongest. The weakest is a dispersion force. In the middle is a dipole-dipole force. And then last but not least, right, the strongest of the three is hydrogen bonding, which, tricky enough, is not actually a bond. Not a bond, but is an intermolecular force. Every molecule has at least one of these intermolecular forces. Every molecule has at least the weakest force. But there are certain qualifiers, certain things that then give other molecules dipole-dipole forces, hydrogen bonding, depending on the way that those molecules are set up, depending on the molecule itself. So let's take a look. First are dispersion forces, which are the weakest of the three forces, like I said before. Every single molecule has dispersion forces. And dispersion forces are basically just the weight of gravity and the intertangledness of atoms and molecules. Imagine you have a container full of ping pong balls, and you need to go get this one from the bottom. It's pretty easy to reach in and grab the very bottom ping pong ball because ping pong balls don't weigh that much, they're not that big, they don't get in the way all that much. But now imagine that these are basketballs, and you have to reach in to get the very bottom basketball. It's harder now. Imagine these are bowling balls, and you need to reach in to get the very bottom bowling ball. Now it's even harder. Imagine that these are a big pile of jump ropes, all tangled together, and you want the one on the very, very bottom. How difficult is that going to be to get through a bunch of other unorganized, tangled jump ropes? Pretty difficult. And yet, none of those things are glued together or are attached together in any sort of way. Those are dispersion forces. The weight of other molecules pushing down on it, the tangled togetherness of the molecules, right, like those jump ropes, that is the representation of a dispersion force. There's nothing actually holding them together. It's just the fact that piling a bunch of things onto each other makes a heavy pile, makes it difficult to get things from the bottom. Right, so if we're looking at intermolecular forces, specifically these dispersion forces, the strength of these dispersion forces increases as the size of the molecules and the mass of the molecules increases. That being said, it is still the weakest of the three. But if I'm trying to compare a little molecule to a bigger molecule, the bigger molecule will have stronger dispersion forces. another thing is the fact that only non-polar molecules are limited to having just this force. Right? If you are a non-polar molecule, and remember, that means a symmetrical molecule. That's our CH4, that's our O2, that's our CO2, these non-polar molecules can never have the other stronger intermolecular forces. If it's a non-polar molecule, it can only have dispersion forces. While polar molecules get access to the stronger forces, and we'll talk about why in a second. If we're talking about dispersion forces, they would be strongest between which of these four non-polar molecules? For comparing dispersion forces, we are looking for a non-polar molecule. We've got four of them right here. We want the one that is the biggest of the bunch to talk about the strongest dispersion forces. And the biggest molecule here is iodine. How do we know? Well, all of these things are in group 7 of the periodic table. All of these things are halogens, and we know that as you go down a group, size increases. Iodine is the biggest molecule of the four, meaning it will have the strongest dispersion forces of the four. Now let's take a look at these stronger forces. A dipole-dipole interaction is the interaction between two dipoles. Now, a dipole itself is the thing that is made when you have a polar bond. When we look at something like SH2, we know that this is a polar molecule. Right? There's only one line of symmetry I can draw, which would be this down the diagonal. And we know that these are polar bonds because they don't connect the same two things. And so if we look, a dipole is the part of the molecule where the electrons get bunched up. Sulfur is a stronger puller of electrons. Sulfur has a larger electronegativity, so it pulls the electrons closer to itself. And that forms the dipole, which tells us that the electrons are going to be up here. Right? Electrons are bunched up here. And then from the hydrogens, there is a lack of electrons, because the electrons are being pulled towards the sulfur. This makes this sulfur slightly negative. Not fully negative, but sort of negative. And it makes these hydrogens sort of positive. And so now when we have a bunch of SH2s together, on top of the dispersion forces, right, the fact that they're all piled up one on top of the other, we also have this magnetic force that's going to keep them attached together. All right, the sort of positive is going to be attracted to the sort of negative of a different molecule. If I drew SH2, these H's are going to be pulled towards the S of a different molecule. And so on and so forth. We now have this magnetic attraction, with these arrows that I'm drawing here, right? This magnetic attraction between the sort of negative side and the sort of positive side, the two dipoles interacting. And that makes it stronger than a dispersion force. Because it's not just them stacked on top of each other, there's also slight magnetic attractions involved. Now we need a molecule to be polar for this. With the polar molecule, we get these dipoles. If it's a non-polar molecule, right, if we look at something like CH4, there is no dipole in here. The electrons are evenly spread throughout the molecule because of all these lines of symmetry, and we know that. And so we need the polar bond and the polar molecule to make this happen. So let's take a look. The last of the three forces is hydrogen bonding. Hydrogen bonding is the three strongest dipole-dipole forces. It's the exact same concept as before. We have a polar molecule, which is going to cause a dipole to form. In this case, oxygen is going to pull the electrons towards it, making it sort of negative, and hydrogen is going to be sort of positive. But for the three bonds here, H connected to F, H connected to O, and H connected to N, the dipole is the strongest. There is nothing stronger than this dipole, or these three dipoles, I should say. This sort of negative is stronger when it's oxygen and hydrogen involved. It's just a sort of positive. It's more, I don't really have a good way of showing that it's more sort of negative. So I just put an extra little squiggly. But these three bonds are the most polar bonds. And so you end up with a very strong dipole, which then when it connects to other dipoles is an even stronger attachment than a regular dipole-dipole interaction. It still has dispersion forces. It still has the fact that they're all stacked one on top of each other, and that makes them hard to separate. But on top of that, it has this pretty strong magnetic force, this pretty strong magnetic attraction that holds the molecules together. Now, really, when we talk about talk about intermolecular forces, it is a two-question thing. We can identify what intermolecular forces a molecule has by asking two simple questions. The first, is the molecule polar? If the molecule is not polar, the only possible intermolecular force for that thing is dispersion forces, because nonpolar molecules only have dispersion forces. If the molecule is polar, we need to ask a second clarifying question. We need to know if that molecule has H connected to F, O, or N. If it does not have H connected to F, O, or N, then the molecule we're looking at has dispersion forces and dipole-dipole forces. Polar molecules have dipole-dipole forces, and everything has dispersion forces. But only molecules with HF, HO, or HN have hydrogen bonding in addition to the other two. So those are the really big questions. Is it a polar molecule? Does it have hydrogen connected to F, O, or N? And by getting the answers to those two questions, you know exactly what intermolecular forces your molecule has. Let's do a couple practice problems. Which one of these three molecules has only dispersion forces? Sure. 1 second. I will answer that question for you, Jordan. Let me just draw this out first, which I don't know why I'm having such trouble drawing this out. Alright, we'll come back to this in a second. Let's go back here. Alright, why are hydrogen bonds limited only to F, O, and N? When we look at a dipole-dipole force, when we look at the difference between dipole-dipole and hydrogen bonding is just an exclusive version of dipole-dipole forces. Hydrogen bonds are the three strongest dipoles. The electronegativity difference between these two, right, H and F, H and O, H and N, is much stronger than any other combination of two non-metal elements. And so instead of, let's put some actual numbers, something like this, right, which you looked at in the dipole-dipole slide, almost the same exact molecule, the same dipole setup. If we look at these dipoles here, because sulfur is not oxygen, right? It's not one of these three. This dipole-dipole, if we want to put some numbers on it and say it's sort of positive, right? We'd say it's plus a half, or sorry, negative a half, right? It has more electrons, but it's not a full bond. It hasn't taken the electrons from the hydrogen, just is not sharing them equally. It's got a half a negative charge, meaning this hydrogen has a half a positive charge. When we look at HF, HO, and HN, the sort of negative is much stronger, which makes the sort of positive much stronger. And these three are the biggest, strongest, most polar bonds that exist. And so they just get this special designation. hydrogen bonding allows for a much stronger magnetic attraction between multiple copies, where a dipole-dipole is still stronger than a dispersion force, but not as strong as these bonds here, or these semi-positive, semi-negative pits. Right, there's no big difference between a dipole-dipole bond and a hydrogen bond. It's just strength. Right? Both of these are movies, but only this one has won an Oscar. Right, they're both still the same thing. They're both the same concept, but this, HF, HO, HN, those three bonds are so much better at doing this dipole thing that they get their own special category. Alright, let's bounce back down to that practice problem. Right here. Which one of these has only dispersion forces? For something to have only dispersion forces and not have access to anything else, we are looking for a non-polar molecule. And so if we want a non-polar molecule, we're looking for the one that has multiple lines of symmetry, which means we are going to pick choice 2 as our answer, because HF is polar, CH2O is polar. What about this one? Which one of these has dipole-dipole interactions? Let me draw these back up for you. Which one of these three things has dipole-dipole interactions? For something that has dipole-dipole interactions, we are looking for a polar molecule. We're looking for something that has only one or no lines of symmetry. And we can find that here in choice 3. This molecule has no lines of symmetry that I can draw in it. It is a polar molecule. And even though it does also have this O connected to H, even though it also shows signs of hydrogen bonding, it does have dipole-dipole interactions as well. Right? They're not exclusive. These only have dispersion. But this molecule, choice 3, actually has all three. everything has dispersion. This is a polar molecule, so it has dipole-dipole. And then because of this OH, it also has hydrogen bonding. It is the only one of our three choices that has dipole-dipole interactions, though, so it makes it our answer. What about this one? Which of these three molecules has hydrogen bonding? Here, for hydrogen bonding, we are looking for a polar molecule, and so that eliminates CH4. CH4 is nonpolar, which means it has only dispersion forces. HF only has one line of symmetry, makes it polar. That's fantastic. That makes it in the running. Only one line of symmetry here in CH2O as well, which makes it polar. Now, to tell the difference, which one has hydrogen bonding and which one doesn't, does this molecule have H connected to F, O, or N? The answer here is no. This is only dipole-dipole at its strongest. It has dispersion and dipole-dipole, while this down here has all three. It has dispersion, it has dipole-dipole, and it has hydrogen bonding. Right, it is H connected to F, so it must be hydrogen bonding as well. Now, why do these matter? Right, why do intermolecular forces make a difference? Intermolecular forces help us when we are looking at the properties of a substance. If I'm looking at something like CH4, which, like we just said, has dispersion forces only, and comparing that to something like water, which has hydrogen bonding, right, has all three of the intermolecular forces, these things are going to have properties that are dependent on their intermolecular forces. Things with strong intermolecular forces have higher melting points, higher boiling points, lower vapor pressures. And things with weak intermolecular forces have lower melting points, lower boiling points, and higher vapor pressures. Because it's more difficult to separate the molecules if they have strong intermolecular forces. If they're being held together really strongly, it's really hard to separate them and cause them to melt or boil or evaporate. Things with weak intermolecular forces don't have that same problem because they're not being held together very strongly. A little bit of energy will help them separate, will help them melt, will help them boil, will help them evaporate. And so if we look at our two examples from before, right, our dipole-dipole example, SH2, and our hydrogen bonding example, water, of these two, water has the higher boiling point, higher melting point, because it has all three intermolecular forces, while SH2 only has dispersion and dipole-dipole. Both of these have higher melting points and boiling points than methane, which has only dispersion forces. And with that, I'm actually going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.